from our classroom. I'll post it to the classroom. So that's why the previous two recording, I couldn't post it in the classroom because first time I try it, when I retrieve it, the file is not good. Second time, the same thing. So I've now recorded it into my computer. Then I will again post it into the classroom. So as we say, the limit here, we have C can be any constant value. So whether S approaches a very small value or a very large value, the answer will be the same constant value. But now, if we have a limit and S approaches a very large value, which is positive infinity, and I have a value divided by S raised to the power P. P can be any value, but the value have to be greater than 0. Because we know if S is raised to the power 0, the answer will be 1. So this means if I have limit S approaching positive infinity and I have any constant value C divided by S raised to the power 0, the answer will still be C because S to the power 0 is 1. But if P is any value that is greater than 0, the answer will be 0. Why? Because we see that we are dividing a constant value by a very large value. So as S approaches too large, C value is going to be reduced, and the lowest it will reduce to is 0 because this is a positive value. And here we are assuming C also is a positive value. So the answer will be 0. So that's the first, our second rule. The first one, we have only a constant value. So even whether S approaches positive infinity or negative infinity, the answer will be still constant value. But now we have X, we have a variable in our function now, the S variable. So now we have to determine if S value is so big, dividing a small constant value by a very big value, and both of them are positive value, the lowest we can go is 0. So the answer will be 0. Now, this is also if X is a very, very, very small value, which is negative infinity. Negative infinity means S is a very small value and N is greater than 0. The answer also still will be 0. So here they say in order to use these three properties to find the limit of a rational functions, you can see 2 and 3 is our rational functions. As S approaches either positive or negative infinity, we first have to divide each term of the numerator with the denominator by the largest power of X. And we're going to see an example what we mean by this. So for example, if I have a S squared plus 3 divided by S to the power 5 plus 2, and the limit approaches positive infinity. Because the highest power is 5, let's say S squared plus 3 over S to the power 5 plus 4. The highest degree is 5. So we have to divide the equation by the highest degree, the X to the, which is S5, everything. Then when we do that, we apply these rules on them, the 2 and 3 rules. Actually, all the 3 rules, if it's a constant value also. So let's see an example how the whole concept works. So we have an example here. Our limit approaches positive infinity. We have a function 2x minus 1 divided by x plus 2. So this means the highest degree is only 1, xx. So we have to divide the whole thing. So that's what we say. The highest power of x is s to the power 1, sx, s1. So we divide each term in the numerator and the denominator by only x. Now, if s is raised, the down is s raised to the power, let's say 3s cubed, then we are going to divide each term by s to the power cube. Then we are going to apply, let me go back, we are going to apply these 3 properties to solve it. So these 3 properties is very important when we are solving. So the techniques here, we can see that it's totally different from what we did previously. Now, if s is approaches, let's say positive 2, it means anywhere I see x, I'm going to substitute with 2 and solve the limit. If s approaches negative 20, anywhere I see x in my function, I just substitute with negative 20 and solve it. Now, if I'm solving it and the answer is 0 over 0, it means I have to reduce the function first. I have to reduce the function. That's where last week we said very important to learn how to factorize expressions, because reducing a function, sometimes we have to factorize the expression if it's a rational expression. But here now we are using different properties. Those are the three properties, the new rules for if limit approaches either negative or positive infinity. So let's see the first step we do. We divide everything by x. So 2x divided by x, 1 divided by, we're going to keep the plus and minus at the same place, nothing changes. The rule said we should divide. When you look at the equation, the highest degree here is 1 because s raised to the power 1. So we use s to divide everything. Then we apply the rule. The answer will be 2 because s will cancel s, I will get 2 here. But remember 1 over x, when s approaches infinity, the answer will be 0. So let's see how it works. Well, first of all, we cancel the x's first. So s, we get 2. S divided by x will give me 1. So we have a 2 and 1. Now, the 1 over x, 2 over x, we have to apply the properties that we learned before. So we can say 0, 0. Because now let's go to the property one more time. So here we say that if we have a constant value divided by s raised to some value here, the answer will give me 0. Whether it's approaching positive infinity or negative infinity, the answer will be 0. As far as the exponent is at least 1 or more greater than 0. And that's exact rule that we apply here. 1 over x is positive infinity. 2 over x, positive infinity. And the exponent is 1. It's positive value, is greater than 0. If the exponent is 0, the answer will be 1 because it will be 1 over 1. S raised to the power 0 is 1, so 2 over 1, the answer will be 2 here. But if it's greater than 0, then everything here will be 0. So we get 2 minus 0, 1 plus 0 is also 0, 0. So we got our 2 and 1. 2 divided by 1, again, is 2. So here we use the property 1 and 2. Property
Can we
3.
go back to the last slide?
This one or?
Yes, this one.
Okay. Yeah. So again, we are using the three properties. When we are solving limits, let me go back one more time. When we are using limit approaching infinity, these are the three properties we have to use. So we can see this is again far different from the previous limit we solved last week. If a limit approaching a value, let's say 10, 1, 3, something, then you just substitute the values into the s, whatever variable you are using. Here, mostly we are using x. So anywhere we see our s, we substitute the value and solve it. And the only thing we should remember is that when you solve it and your answer is 0 over 0, it means you have to reduce your equation. If it's 0 over value, then the answer is 0. If it's a value by 0, that means the limit does not exist. So those are the three rules we went through last week. If we have a limit approaching a value, we have three options. If it's 0 by 0, reduce the function. You are going to get a good answer. If it's 0 over a value, then the answer is 0. But if it's a value by 0, that means the limit does not exist. There's a discontinue in the function at that value that we have where the limit approaching. But when it comes to infinity, these are the three properties we are going to use. And we can see how the step work here. So let's try one more time. This is our question A. The limit approaching again positive infinity. and we look at a function. What is the highest degree, exponent degree? It's 1, because we have 2s and x is 1. So this means I'm going to divide all the 4 terms here by x, because that's the highest exponent, the degree. So that's what they said here. The explanation is here. And so that's what we did now. We divide 2s by x, 1 by x, s by x, 2 by x. Then we see if we can cancel. Yeah, this one we can cancel s, we cancel s. So here we will get 2. S can cancel s again. Here we get 1. But s cannot cancel 1. So we have to go by the property. The property tells us that if s approaches whether positive or negative infinity, and I have 1 over x, and the exponent of the x value is greater than 0, in this case is 1, then the answer will be 0. So we get 0 for both of them using property 1 and 2. So the final answer is 2. Now let's look at the second one. Okay, so this is again, you can use your calculator to plot the function. So this is the original function. We can see that the reason why we get 2 here, it means we are going to, when we plot this function, we will see that in the -2 section, we're going to have asymptotes on the x-axis. But our answer here is for y, because f at s is the same as y. When we look at the y-axis, we can see that our function can never touch the line. It will never reach y when y equal to 2. So it will look something like as we can see. Now let's try the second one. So that's what they are explaining here. Our answer 2 means we are going to get a horizontal asymptote. So the second question, we see that our highest exponent is 2. So we have to divide everything by s squared. We have x, which is the exponent is 1. We have s squared, the exponent is 2. And the highest again is 2. So we divide everything by s squared. Always we divide by the highest exponent. Then here we have s squared divided by s squared. We get 1 here. But here we get 3 over s squared. Here we get 1 over s squared. We cannot cancel. And here we have s divided by s squared. So we get 1 over x. Then we apply the properties. So now we can see 3x squared cannot cancel. 1 by x squared cannot cancel. And 1 over x, because we cancel only 1x at the top. And we still have 1x left. So the same thing as we did previously, the remaining values, we are going to get 0. Here we say that this limit does not exist because the numerator approaches 1 and the denominator approaches 0. But let's go back the reason why they said the limit. Even if we plug in the value, you will see what will happen here is that we said that we cannot divide any value by 0. Even if you use your calculator, if you divide 0 by a value, you will get 0. But if you divide a value by 0, you will get nothing. So what happened here? We get 1 plus 0 over 0 minus 0. So we get 1 over 0. 1 over 0 means the limit does not exist. Only here, the slide here, they didn't plug in the zeros, but we can see that everything here is 0, 0. So we went straight, we said that the limit does not exist because the numerator approaches 1, which is, but the denominator is what? Approaches 0, because we can see 0 zeros. And here will be 1 plus 0, which is 1. So we get 1 over 0. 1 over 0 means the limit does not exist.
Can you go back to those 2 slides back?
So again, we are using those three properties. When we have exponent as our denominator and variable, the highest exponent is what we use for the variable to divide them. Here it says square. So the exponent is 2. That's the highest degree of the variable. So we use it to divide everything. First one, we get 1, so 1. But we cannot cancel 3 divided by x squared. So the rule said if we have something like this, since the exponent is greater than 0, the answer will be 0 here. Exponent is greater than 0, 0. Exponent greater than 0, 0. So you get 1 over 0. Any value divided by 0, the answer we don't have no answer. So the limit does not exist because the numerator approaches to 0, but the denominator approaches to 0. So 1 over 0, no solution. So if no question, let's look at this rule also. Here we have limit at infinity and also horizontal asymptotes. So here we say that if a limit approaches infinity, f at s equal to b, or limit approaches negative infinity, f at s is equal to b. B can be any constant value. Then we say that the line y is equal to b, and that will be the horizontal asymptote. And that's what we got. The first question, the answer was 2. So when we use the calculator to plug the function, you see that the function will never touch where y is positive 2. So that's horizontal. Again, there's no any rule here. What they are trying to explain is what we did in the second question, the limit does not exist. But in this question, the limit was 2. So the answer we get to from the question here, this is the question A. If we solve this, the answer will be 2. But since the limit approaches positive or negative infinity, it can be positive or negative infinity. The answer we get here will be horizontal asymptote. So when we look at the function, we can see the 2 horizontal. So the function will never touch the 2. It will get close to it, but it will never touch it. And that's what they are explaining here for us. What is it? I think it's this one. Let me see it. So here you see that when we solve the second one, we say the limit does not exist. So this means if we plot this function, there will be no horizontal asymptote. So you can see here, we only have a vertical. We don't have no horizontal because the limit does not exist when s approaches either positive or negative infinity. We don't have no limit. So that's what there's no horizontal asymptote to note. All this, there's only a vertical asymptote at s equal to 1. And that's what they explain to you also. All we are looking for is the horizontal asymptotes if the limit is approaching either positive or negative infinity. So we also discussed about continuous functions and limit at any value. So it's the same concept here also, continuous function with a limit at infinity. We say the following information can be useful in discussing the continuity of a functions when the limit approaches infinity. So if we have a polynomial function, as we said earlier, if you have a polynomial, the polynomial function means it's not divided, there's no denominator, and there's no square root. We know that the limit or the function will be continuous everywhere. So the limit will exist in any value we get. if we have a function that does not have no denominator, no square root. Because when a denominator is 0, then we have this discontinuity. If a square root value is negative, then we have a discontinuity there. So with a polynomial function, the same concept. As a limit approaches any value or infinity, we always have a limit exists throughout. But if we have a rational function, which is look a form of we have a numerator and the denominator, f at x divided by g at x. We know that we don't want g to be 0. If g is 0, as we saw in our second example, the limit does not exist. So here we say that if g is not equal to 0 at any value of s, then the function will continue. The limit exists, it's continuous everywhere, as far as g is not equal to 0. But if g equal to 0, then the limit does not exist. So that's here. If g at c equal to 0, then the function is discontinuous. If g at c equal to 0 and f at c not equal to 0, then we have a vertical asymptote at s equal to c, but we don't have no horizontal. This is if s approaches infinity. Now, if g equal to 0, g at c equal to 0, and the limit s approaches c, the answer is L, then the graph has a missing point at c and L. We still get a solution. The solution is L. But since g at c is approaching 0, we will still have a missing point. And a piecewise function, we went through that. Defined function may have a discontinuity at any s value where the function changes its formula. So it's the same as what we studied last week about piecewise function. Also here they say the following steps is very useful when you are evaluating limit at infinity for a rational function, such as p at x divided by q at s. First, they say we should divide both p at x, which is the numerator, and the q at s, the denominator, by the highest power of x. And that's what we did, highest power of x, find in either polynomial. Then we use the property of limit at infinity to complete the evaluation. So these are the two steps we just did for the two examples. Always when the limit approaches infinity, this is the step we have to use, whether positive or negative infinity. But if it's approaching again a regular value, then we substitute with the regular value. We don't need to divide by the highest power of the x. So that will be the conclusion for 9.2. Wait for a few seconds if we have any question before we move to 9.3. So if no question, then we start 9.3. So in 9.3, we are now getting close to starting derivatives. We finished with limit. We saw the two types of limit, either s approaches a regular value. The steps we went through that. You need to factorize if you have 0 by 0, etc. We went through that. Then when s approaches in positive or negative infinity, different method altogether to solve. It's only two steps. Divide all the expression. If it's a rational expression, divide. That means we have a value divided by another value. Then that's numerator and a denominator. So we divide the highest degree of the x for all the terms. Then we apply the three properties of when limit when s approaches infinity. So again, we finish with limit. Next section, we're almost getting close to derivatives. But the concept of derivative, actually the concept of calculus, is you are trying to solve a problem when there's a change going on. So something like rate of change. Calculus deal with changes of activities in our real life. For example, you are driving a car from one destination to another. You want to know the rate of change, how long it takes to reach. Maybe it will depends on the speed, or the speed will depend on the time you reach, etc. So first we will go through the concept of rate of change. Then from there we'll move into derivatives. So the whole concept of derivatives is finding the rate of change of a function, moving from, we have a function, the interval is from A to B. The function is, if the function is linear, then the rate of change is constant, which is same as the slope. But if in calculus, the function is not constant, it's not linear, it can be any type of function. So this is where, again, we need to find the rate of change. So in this section, we're going to learn how to find the average rate of change, then define the derivative. As we said, derivative is the same as a rate of change concept. Then we're going to use the definition of derivative to find the derivative of a function, and that will put us to derivative topics. Then we can use derivative to find a slope of a tangent to a curve. We know a slope of a linear, you just take 2 points on the linear line or the line, take any 2 points and find the slope. But if you have a non-linear, if you have a parabola or any function that is non-linear, we can see that the rate of change will not be constant on the line. Some may go up, some may go down. It's a curve. So in that case, we have to come up with a concept of solving that problem. So we use something called the tangent to the curve. We draw a straight line to touch the curve. Then we take the points from there. So we can have one curve. The slope can be different values because the rate of change is different in different points or different interval on the curve. So let's start with the average rate of change first. And we said here for linear functions, again, average rate of change is constant because all the points will be on straight line. So just take any 2 points. It doesn't matter the location you take it because it's constant. So we have seen that slope of a line measure the average rate of change of function can be found from any 2 points on the line. But if the function is not a linear, the slope between different pairs of points no longer always give the same number. So this is where calculus, the beginning of calculus starts. In algebra, we have a straight line. The slope is constant everywhere in the line. But if the line is not straight, the slope will change in different interval of the function. So here we need to find average rate of change. So this diagram will help us. We have a function. We can see that this function is non-linear. It's kind of like a halfway parabola. The interval is from A to B. So when we see the interval A to B, our function is the black, it's not linear. But if I want to find the average rate of change, I will draw a straight line, that's the red line, from point A to point B. So I'm finding the average rate of change on point A, point B. Now here we say it's average. It's not the actual rate. It's approximately, I would say, the mean, the average rate of change. Maybe some small part will be higher, some other part will be lower, etc. But average rate of change for that nonlinear line. The formula slope, again, we are using slope as m, and the notation is m. It will be the function when s is b minus the function when s is a divided by b minus a. So that's the formula to find average rate of change, f at b. B can be any interval. Actually, here we have the interval. This is b and this is a. So A will be any value to B. Now, if the function is x squared minus 2, then that means, and the B is, let's say B is 10 and A is 2, then we just substitute B 10 into the function and A to the second one, then find the difference of the two. Then the down will be 10 minus 2 because B is 10, A is 2. So again, that's the formula to find average rate of change. The whole concept is explained here. We are looking for a slope, but since it's not a linear, the slope will not be a constant on the line. So we draw a constant line to touch from the beginning of the function to the end of the function, A to B. Then we find the average rate of change here. So we start with one example. This example said we have a figure 9.8. Again, this is from our course textbook. And it shows the percent of elderly women and of elderly men, women and men in the workforce. This was selected from 1970 to, they projected it to 2040. So we have the men will be, again, we can see the legend of the graph. Men is blue, women is pink. So we have 1970 to 2040. They gave us the value, the projected value, and the actual value is from 1970, let's say, to last year was 2020. So 2030 and 2040 is projected or predicted. Now with this here, we can see that this is not a straight line. The slope, the interval between, if we find the difference from 1970 to 1980, it will be different from if we find 1980 to 1990. Most likely to be different from 1990 to 2020. So this is not a regular slope whereby we will say that the difference is the same every 10 years. No, they are different. So here we can say, okay, let's find the average rate of change between 1970 to 2000. So that would be 2000 minus 1970. Let's say for men. So men will be 19.5 minus 26.8. We can see that there's a decrease here. So the answer will be negative. In 1970, we have more men in the workforce than 2010. So that's the whole concept of average rate of change. But let's solve the one the book tells us to solve here. So yeah, they say we should find the average rate of change of a percent elderly men in the workforce and also elderly women in the workforce from 1970 to 2040. So I'll look at 1970. Okay, so we're looking from 1970 to 2040. So we can find the difference of 2040 and 1970. For men, the difference of 17.3 and 26.8. The answer will be negative because we can see decreasing. For women, the answer will be positive. It's 10.1. 1970 was 9.7. So it increased a little bit. So let's see the solution here. So change in percent women, men, the answer again is negative because in 2040, we have 17.3. In 1970, we have 26.8. So the difference of 17.3 and 26.8 is negative 9.5. The difference of 2040 and 1970 is 70. When you divide the two, approximately we have negative, let's say roughly 0.136% points per year. So I'll wait for a few seconds if we have any question. Okay, average rate of change, take the 2 points. Any 2 points. Here we are looking from 2040 to 1970. So we take those 2 points. And the Y will be the vertical. So that's our percentage, 26.8 and also 17.3. Women, let's see, the women will be positive. 10.1 was 2040. 9.7 was 1970. So we get positive 0.0057%. Okay, if no question, we keep going. So we're going to move to what we call the instantaneous rate of change, velocity. Is the same concept as velocity. And here we say we can represent the change in time by h. So we're going to use h notation. Then the average velocity from s equal to 1 to s equal to 1 plus h, because the time difference. If it's 10 minutes, we start from 1 minute. So if it's 10 minutes, then h will be 10. So it will be between 10 to 11. And approaches the instantaneous velocity at s equal to 1 as h approaches 0. But as we said, h can be positive or negative value. So let's see an example here. Now the question here, suppose we have a ball. We throw the ball straight upward so that its height f at s in feet is given by the equation. So when I throw the ball upward, where the maximum place it reach in the air, that will be the height from the ground to the air before it drop down, the maximum height. Sorry, I say weight. The maximum height it reach in the air before it start to drop down is the equation given here. And x will represent the time it takes. The time it takes to reach that height. So now the question here said that we should find the average velocity from s equal to 1 to s equal to 1 plus h. Then secondly, we're going to find the instantaneous velocity at s equal to 1. Here we use the same concept of average rate of change. But the first, we have to use the interval given here. The second, instantaneous will be a particular point. So here when s is 1, s is time. So let's say it's 1 minute or 1 second or 1 hour. They didn't give us, oh no, sorry, it's in seconds. S is time in seconds. So here we want to find the instantaneous velocity when s equal to 1 second. The average velocity will be from one time to another. So when s is 1 second to when s is 1 second plus h. So let's see how we solve this problem. Again, we are using the same concept as average rate of change. So here we say the h will represent the change in x time from 1 to 1 plus h. Then the corresponding change in f at s height is this. So we have, first, we are looking for f at x. S is 1. Second, we're going to look for f at s plus h. Remember, the average rate of change will be f at b minus f at a. F at b is 1 plus h because from a to b. So we have 1 plus h, so it's b minus 1. So it's the same concept here. This question is like a physics application. So we start from 1 second to 1 plus h seconds, so a to b. So we are looking at the top, we're looking for the average rate of change at the top first. F at b minus f at a. B will be 1 plus h. The beginning a is 1. 1 to 1 plus h, a to b. So we just plug in the value. So first we're looking for 1 plus h. So in our function here, anywhere we see x, let's go back once. So anywhere I see x, I'm going to have 1 plus h. So I'll get 64 times 1 plus h and 16 times 1 plus h squared. And that's what we have here. 16 times 1 plus h squared. and 64 times x. S is 1 plus h. The second equation is easy. Its effort is 1. So anywhere I see the equation, I'll get 96 plus 64 times 1, 16 times 1 squared. So 1 times any value is the same value. So that's why we have 96 plus 64 minus 16, because we substitute with 1. 1 times any value is the same value. So now we can open the parentheses here. Then we combine the two expressions. And this is what we get. 96, 64 times 1 is 64. 64 times h is 64h. Minus 16 times, first of all, 1 plus h squared will give us 1 plus 2 times 1 and h. So it will be 2h plus h squared. This is the perfect square. So we should know this in college algebra or pre-calculus. 1 plus h squared is perfect square to give us 1 squared plus 2, 1h plus h squared, which will give us 1 plus 2h plus h squared. Then we add all this together, 96 and 64. We take 16 out of them. That gives us 144. So I'll wait for a few seconds. If up to here is okay. Okay, so if no question, we can open the parentheses here now. And that's what we did. 16 times 1 is 16. 16 times 2h will be, again, it's negative positive. So it will be negative. Negative positive again to be negative times minus 16h squared. So we have minus 16h squared. Again, there's a little bit step missing here. They already, again, here, assume everybody can do this. Open these parentheses, then combine the like terms. So when they open the parentheses, we have h, 64h positive. We're going to get minus 32h, and etc. So we combine all the like terms, and the final answer will be this. So we get 32h minus 16h squared. Okay, so if no question, I'll move on. So this is only for the numerator, the top. Now we need to find the down. The down will be, remember, f at b minus f at a over b minus a. B is 1 plus h minus a. A will be beginning, because the question said the changing is from 1 to 1 plus h. So it will be 1 plus h minus. So then we plug in the values. 1 plus h minus 1, of course, 1 will cancel the 1, so it will left with h. And previously we do the numerator. This is the value we get from the numerator, the previous steps. So here we can cancel the h, because we see that h and h squared is common. So we can cancel the h out. So our final answer will be 32 minus 16h. This is the average rate of change. Now, if they say we should find the instantaneous value will give you at a particular value of x. So that's the next step. Here, instantaneous value v is the limit of average velocity as h approaches 0. So we take the limit of it. And h approaches 0 means everything here will be 0. So our answer will be 32. So this means the speed, the instantaneous velocity is the speed. It will be 32 feet per second. And that is what is leading us now. We are getting close to derivative now. So all the derivative formulas came from this formula. So here they say we should know that average velocity is found over a time interval. The first question, average velocity, we find it between 1 to 1 plus h, a time interval. But instantaneous velocity is the same as called the velocity. It can be found at a particular x time, or in this case, we are using time, so at any time x. And this is the formula we are going to derive all our limits. So yes, suppose that an object is moving in a straight line and it has a position of y at a time s given by y equal to f at s. Then the velocity function will be this. As the limit h approaches 0, f at s plus h minus f at x over h, provided that the limit exists. Now, this tells us that derivative is based on average or rate of change of something. In this case, a velocity function, rate of change. And that's the formula here now. So you can see they tell us from the velocity point of view. Here now we start our derivative. So a derivative, if f is a function defined by y equal to f at s, then the derivative of the function will be f apostrophe. So this symbol means derivative of the function will be the limit h approaches 0, f at s plus h. So this is the formula to find a derivative. But maybe some of you know calculus already. Now, when you are using this to find a derivative, you're going to waste a lot of time, especially if the function is very big. So from this, we were able to derive all the rules for sum, multiplication, division, addition, power, everything. But everything comes from here. So if we have a question, the question said find the derivative of a function 2x, use the limiting process. If they say we should use the limit process, you have to use this formula, the limit process. Otherwise, you use the derivative formulas, then you use the regular derivative formulas. So this is a limit process to find a derivative of a function. Whether it's addition, subtraction, multiplication, power, it doesn't matter. This formula will work for everything. The problem is that it's a long process. It's a long process. So this is an example given here. So we have a derivative y equal to f at x at any value x. Here, the first step, they gave us the 4 steps to do. The first step, we let h represent the change in x from s to s plus h. Then the corresponding change in y equal to f at s will be, if I have x, we change derivative against the rate of change from one place to another. So we're going to use the notation s to s plus h. So if my interval is s to s plus h, remember average rate of change, I should get f at x, and also I should get f at s plus h. So that's where we get here f at s plus h minus f at x over h. So you can see that this is exactly the same formula we just saw for velocity, the same formula. So we are moving average rate of change from one position to another. So that's why we always say calculus, the goal of calculus is finding the rate of change of anything. It can be in the business, finding the rate of change of a price of a goods from 1 month to the next month, or stock price. Stock prices can change every minute or seconds. You find the rate of change of one stock price of a company from 1 second to another second, or 1 minute to another. We can use calculus to find it. As far as we know the interval, the time period, and we know the first price to the second, again, we can be able. So that's the step. Now let's see the example here. Here we have a function f at s equal to 4s squared. Now find the derivative of this function. Now if I'm using the formula, if you know the formula in your head, you can just tell us the answer. The answer will be what? 8x. That's it, 8x. Because we have a power rule here. The constant, you don't touch it. The power rule said you multiply the power by the value, the coefficient, then you subtract 1 from the power. So the derivative of 4x squared will be 8x if you are using the formula, which hopefully we will start on Thursday. But if you are using the limit process here, this is the process you have to follow, which means we have to find f at x, then we also have to find f at x plus h. So you find f at x plus h minus f at x, and we plug in the values. Is 4s squared. So anywhere I see s, I'm going to replace it with s plus h squared minus f at x. So s is s squared, so you just put minus 4x. Remove the parentheses. This is perfect square. Then multiply 4 by everything inside, minus 4x. Combine the like term, you get 8sh plus 4h squared. So this is the answer for f at s plus h minus f at x. Then we remember the formula we have to divide by h. So we divide everything here by h. Luckily, h will cancel. H is common in both terms, so h will cancel out. We get 8s plus fh. But remember, we said the limit is when h approaches 0. So when h approaches 0, 4h will be 0. So the answer will be 8x. But look at the long process that we go through. But if I know the formula in my head, as I said, the exponent is 2, multiply 2 by the coefficient, so it will be 8. Then subtract 1 from the exponent, so the answer will be 8x. That's if I'm using the formula. So again, in the future, the quiz or homework, if we have a question like this, we may say, okay, find the derivative of the function using the limiting process, which means we want to see all these steps, limiting process. But find the derivative of this function using the formula. Well, using the formula, you just write 8s because that's the formula. And hopefully we will go through that on Thursday. So these are all it seems like it's almost time. I don't even look again, my screen is, it's time, 9:46. Okay, so we're going to end here. Now, hopefully we continue this section on Thursday. So Thursday, we're going to start the derivative. We're almost starting now. The derivative almost, this is the beginning of it. So actually, let's finish this slide. It's only 1 minute, then we're done. So hopefully Thursday we start to solve example. This is just the theory. So in this textbook, we can use any of these notations as a derivative of a function. So dy dx is finding the derivative of a function y. Or we can use y prime here. This is derivative. These are all the symbols of finding. Then also, this class is a business calculus. Most of all the applications problem we are going to solve, it will be related to business problems. So if they say we should find the marginal revenue for a product, the term marginal means we are looking for the derivative of the revenue, the change of the revenue. Average rate of change of the revenue. We use the term marginal. So if I have a question and they say, okay, the function of the revenue for the product is 2s plus 1. Find the marginal revenue. That means you find the derivative of the revenue function. And so that's the formula for marginal revenue. You can see it's the same as the limiting. So if they said you should use the limiting process, then you have to use this formula, the same formula we just used. As I said earlier, this is the formula to find any derivative of any function, but the process is long. In fact, look the example here. We're just looking for the derivative of 4s squared, and look the process we go through. Now imagine if they say we should find the derivative of 4s squared plus 2sy, plus 2x plus 7 divided by 8s cubed plus 4. Then it will be a long process. We can't even write it. We will not can't solve it. Maybe to take 30 minutes, but you have to solve all this rate for each file. It's impossible. So we're going to use the formula when you reach to a more complex functions. So I think we can end. So let me look how many slides left if we can finish this before Oh, it's a lot, 37 slides. So we are at 21. So we're going to end here. Then hopefully Thursday we continue from slide 31 in 9.3. Again, if you have your textbook, this is 9.3 chapter. So I'm going to wait for a few seconds. If we have any question before we leave, I'm going to stop sharing my screen.
Is there any update on if we're gonna have a hybrid class or not?
At the moment, we're holding to it because of the issues now. So with the current pandemic issue, so hopefully I will hold on to maybe after next week we may know for sure. After next week, so this week I will do online. Then next week I may decide if I should go. Everything depends on the professor, because the school said one thing the required is that we have to do online. You have to be synchronized. So that means we have to meet live in a class. That's the required. But for the campus, it's up to the professor. If the professor feels there is safety, then we can do it. For example, I teach in another school. The school now, the requirement for the school said, or if you want to take a class in the campus, every student must bring a COVID-19 test negative evidence for a period of a week. So that means every week you have to go and test, which again is too much. So far, our New Jersey City, I never heard about the test result. The only thing we have to follow the social distance protocol and everything. So just hold on. Let's hold on for another. By end of this week, I'll see how things is going. Then I'm the one who have to decide whether to give the class in campus or not. So far, I have only one student that sent me an email that he will prefer, he or she, I can't see the name, I can't remember the name, he or she will prefer to have a hybrid, high-fresh class. So for only one student. So if you are still interested, if we get enough, then it's up to me to make the decision. Should I go? Up to now, the school didn't say we have to go. If the school said we have to go, then I have to go. But that decision is up to individual professors. But the required is we have to meet synchronized in a classroom, a live class every time. I hope I answer your question. Okay, so if there's no other question, then again, we will meet synchronized in the classroom here. And I will see everybody on Thursday. Again, we have assignment that is due today. And also I went through the steps how you can submit the assignment. So I'll wait for a few seconds if any question about the assignment. Other than that, then we see on Thursday if no question. Okay, so I'm going to leave the classroom. Okay, so everybody have a good day and I'll see you on Thursday.